Okay, welcome everyone. So last week we had the special lecture by Andy, and this week we have the proper Kavli lecture, formal lecture by, and we are very glad to have Claudia Maraston giving the lecture. Before we start with the introduction and the presentation, let me remind you all to keep your microphone muted, and that the presentation will be recorded, but not the question and answer session. Okay, right. So again, welcome Claudia virtually. Claudia graduated in Bologna, and then she was in Munich at both the Maximilian University and the Max Planck Institute for Astrophysics. And then she was in Oxford with the Marie Curie Fellowship, and then she moved to the University of Portsmouth, where she's now professor of astrophysics. And she's been given various awards, including 2 years ago the Eddington Medal from the Royal Astronomical Society. The area of expertise of Claudia is the development of the most advanced, I would say, models and models for stellar populations in galaxies, which she used, as well as many other teams across the world, to investigate the properties of galaxies, the evolutionary mechanisms, the content of dark matter, and many other applications mostly focused to understand the physics of galaxy evolution. And she's been also the architect of the Sloan Baryonic Acoustic Oscillation Survey, BOSS, and she has also had a key role in many other projects. And I believe today she's going to talk, give us a summary of her findings through her various fantastic codes and applications to Sloan, and I think also to other datasets. So Claudia, if you are ready.
Thank you, Roberto, for this lovely introduction, and thank you very much to you and to Alice Concas for actually organizing this lecture. I'm very, very honored to be here. I'm really impressed. So yes, so I will share my screen, and we have tried it. It worked before and hopefully still work. If you give me your okay, I can start.
Please go ahead.
Brilliant. So, as Roberto said, the request was to describe what has been my work and the development in the field. And since the PhD, my main occupation has been to try to develop and advance what is called evolutionary population synthesis, and I will have the opportunity to describe them in detail. As Roberto mentioned, this research finds the most obvious application in the study of galaxy formation and evolution, and as I will have the opportunity to mention, also in cosmology and stellar evolution. You know very well that the history of the cosmos has been dark for the first 380,000 years, after which we actually witnessed the development of galaxies, the first stars, possibly their collections into galaxies, maybe first a small galaxy, then big galaxies, and this has taken most of the lifetime of the universe. So galaxy formation and evolution is at center in modern astrophysics. As we also know, it is quite a complicated process because there are many events that participate to the formation and evolution of galaxies that indeed they were at the time of my PhD, and they are still relatively poorly known, and there is much investment, in fact, in trying to understand them, possibly from first principle. And I alluded to the conversion of gas into stars. We cannot go to a class of students and teach them and write an equation with a simple formalism to explain how you convert a certain amount of gas into stars. There is important feedback, obviously, from stars with the copious UV emission, but also from massive black holes, which came into importance maybe 20 years ago, which is still poorly understood and modeled, but not entirely in a self-consistent manner. We also think the universe is mostly composed, or let's say for 36%, 30% by dark matter, whose constituent we don't know, and we think that dark matter merging drives a part of the overall process of galaxy formation and evolution, and again, there we have difficulties. Another important process that it was understood relatively recently, Roberto Maiolino and his group are very active in this, in how actually you stop star formation in galaxies, considering that dying stars keep emitting gas. So all of these aspects are in fact requiring much research, such that when we have a beautiful field of galaxies, such as the Hubble field, I really always like that, what do we want to know of all these little dots in the sky that can be as distant as 10 billion years? We want to know, of course, their distance. We want to know possibly their age at the time of viewing and the formation up to then. What was the history of stellar formation, which determined a lot of other characteristics, including the chemical evolution? How much mass is in stars? How much is in dead stars? Which help us then constraining the amount of mass that we don't see. It's easy to understand that all these quantities are actually related, and we should be able to infer them, but the only instrument we have is to observe the light emitted by these galaxies. Here I'm showing a spectrum for the Sloan digital sky survey. Beautiful, you see lines from many elements in great detail. Now, instrumentation can also allow us to see this spectra at high redshift, but ultimately we need to extract astrophysics, all the information that I mentioned, out of this. So the brief outline of my talk will be, I will introduce the stellar population model, which is the tool out of which you derive the information, the physical parameters that I just quoted, crossing an overview and coming to the state of art and very recent development. And then I want to actually focus on a few key applications of these models. So we needed to tribute to the first attempt to calculate the integrated spectrum of a galaxy through the technique that Sandy Faber put forward in the 70s, which is called optimized population synthesis. At the time, also followed by Bob O'Connell and Eduardo Bica in Brazil. The technique is relatively straightforward. I should already mention it is still used nowadays. And effectively, the calculation of the whole galaxy spectrum is obtained by combining with ad hoc adjustable coefficient spectra of individual stars. They can be theoretical, or even better if they are empirical, in a sense that they are probably more likely to recover all lines at a certain accuracy. The weights in this technique are arbitrary. The scope is to obtain a best fit. They are still used, as I say, in data analysis pipeline, like in the Sloan 4 pipeline for kinematics, emission lines, and redshift, when it is not needed to know the physics of the object we are trying to constrain. Because obviously, model constructing like this do not allow us to make prediction as a function of cosmic time. And also, they might be aphysical in the sense that in order to obtain the best fit, we may combine spectra violating rules of stellar evolution. Still in the 70s, there was another approach that was pioneered by Beatrice Tinsley entirely through a series of papers, which she called correctly evolutionary population synthesis, where instead the knowledge of stellar evolution that at the time was coming up through stellar evolutionary tracks from the Padova group, from the Yale group, and for a few groups in the world, it is through stellar evolution that we find the coefficient to possibly weigh the luminosity of stars in different evolutionary phases. Those stars that we are never being able to actually see in distant galaxy, but we know they will be there. Excuse me. Sorry. So in this approach, that is the physical approach to the calculation of model spectra, the contribution of stars in different phases is actually weighted by energy and time scales, according to a rule that then became famous as the fuel consumption theorem, as named by Professor Alvio Renzini, who is in the center of these photos, in 1980s. This approach in particular has been followed by people who have been working closely to Alvio Renzini, like myself, but there are several there is another approach that has been pioneered by Gustavo Brusual, who is the gentleman in the photo with myself at the end of the in the top right, which is called isochron synthesis, but nonetheless the idea is still to exploit the knowledge of stellar evolution. So I will focus on the virtues and the properties of these models. There are a few model input physics that are important to recognize that actually then affect the quality of this model. Obviously, we need to know the energy emission per stellar mass in the various evolutionary phases. And it should be noted when Beatrice Tinsley started to calculate her first model, stellar tracks barely exist above the turn-off. The red giant branch was actually a very difficult part to be included. The other thing that we needed to, the other input physics that we needed to describe well are the spectra per each location in the HR diagram that is where the stars are energetically relevant. We then need a distribution function to define the mass distribution of our hypothetical population in terms of low mass versus high mass stars. I would like to add that we also need a distribution of stellar remnants, so the masses that will end up in white dwarf, neutron stars, or black holes. There are a few other effects. I will be able possibly to show a few slides on that have been added more recently. They are not directly connected with stellar evolution from first principle, and in that they are more complicated to involve. But this is not to say that they are not important. And these are binary stars where actually people in Cambridge have actually played an important role, emission lines and nebula continua. So energy and time scale, of course, come from calculation from stellar model, stellar evolutionary model. And here I show from my paper 2005 that there is still variability, and I believe this plot is still valid, between especially the run of the red giant branch in terms of luminosity, but mostly temperature, between various computations. Here I show popular computation like the Padova track, the Yale track, the Victoria track. There are a few uncertainties that, as I will show, are of even cosmological importance in determining the ages that we derive for galaxies, or the exploitation of stellar evolution for cosmic chronometers, cosmology. They are core convecting overshooting parameterization, mixing length parameterization, and the equation of state. Regarding the last, this is a plot that is very new, and one of our students is preparing, that is actually pushing this comparison down to the very dwarf main sequence. And look at the gravity. We go down to gravity 5.4 and very cold temperature, using data from Sloan that I will have the opportunity to introduce later. But what I want to stress you is the large discrepancy in dwarf main sequence stellar evolution prediction, here from the Dartmouth versus the Padova tracks, with the Dartmouth actually running completely through these newest generation data. So let me say, we try our best in this model. There are few aspects that I would not say we know perfectly by now. The other crucial ingredient is the stellar spectral energy distribution that we associate to a certain energetic in order to obtain a description of the integrated spectrum of a galaxy. And again, the choice can be to resort to theoretical spectra from model atmosphere. I use them routinely in my model. They give us a lot of advantages. Their resolution is arbitrary. We can go very high resolution. The wavelength coverage does not depend on instrumentation. In principle, we can model any arbitrary parameter. However, as known, there might be inaccuracies in line list. Here I show a comparison that for a work I'm doing with Manuela Zoccali, looking at individual stars in detail. In the upper panel, you see a giant star where the data, the black and the red is the best fit that we obtain with one of these highly sophisticated models. And there are a lot of lines that are titanium oxide lines that are actually not included in the models. And they could actually create some problem in the modeling of extragalactic system. While the dwarf part of this model is actually pretty impressively matching well the data. But this is just to say we have leverage, but there are also problems. So what people have started to do maybe a decade ago is to try to collect empirical databases of real stellar spectra, of course, from the Milky Way, where there are other problems like the signal to noise of the spectra, how many we can actually collect, etc. But the spectra will contain the lines that are actually present in nature. Here I show a plot from a very recent library in which I am much involved. The first library of stellar spectra based on the Sloan telescope, which is a proprietary telescope that could obtain thousands of spectra, and effectively not even thousands, tens of thousands. The number we have now is 30,000 spectra with high signal to noise and a high resolution. This is going to be the largest library ever made, I think, for time in the future. And you will see, you see how beautiful spectra for cold stars we are obtaining. I will have the opportunity to get back to this library in a few slides. There is another ingredient that for the models is just a free parameter, which is the initial mass function, the distribution of stellar masses at the birth of our hypothetical population, and how they divide themselves in low mass stars and high mass stars. Everyone knows about the initial mass function, and I just want to briefly mention that usually the standard model are including a mass function that is ranked anchored to observation of the solar neighborhood, but in recent years there have been researchers exploring both using mass function that are bottom heavy at the low mass end, as the group around Corot and Van Dokkum for massive galaxy, as well as top heavy for high redshift starburst, like in some galaxy formation models. And now, this is the only movie you will see from me because I'm one of the old style researchers. This is now the result. We have calculated stellar population models. This little movie shows you effectively our latest model based on this very large library. But what you see here is how the spectrum changing according to the age. The plot started when the population was very young. The different colors show the metallicity. The fluxes are realistic and normalized to certain solar masses. So these spectra are very nice to see. Now we need to understand whether they will allow us to actually perform robust astrophysics. So the first thing that a code like mine, based on the fuel consumption theorem, allow us to model each individual stellar phases in detail, and especially have a sense of the energetic budget of each stellar phase. This turned out to be very useful also in order to identify uncertainties in the model. So I think I want to show you, because it's very instructive. If I start from the total spectrum of a 5 billion years old population with solar metallicity, which is the black line, this is just a measure of the emitted energy as a function of wavelengths. The contribution in real units, so this is scaled up by the main sequence stars of core hydrogen burning, is visible as the blue line. The contribution by the subgiant branch is the magenta line. The red giant branch is extremely contributive at this age, is comparable to the main sequence also in the optical, and then taking over, of course, in the near infrared. The horizontal branch peaks, depending on the location of it, which is a function of mass loss, around the same wavelengths. And finally, the early asymptotic giant branch at this age is, this is the type of asymptotic giant branch that contribute. It's very red, although you can see it in this squeezed slide. However, the energetic contribution is around 5% of the total bolometric. This is, of course, as a function of age, and this relative contribution will change with the age of the population. This is just an example of how it is a good practice to calculate model for which you can trace back the actual input physics. Now, what I've shown you so far is the simplest rendition of this model, which postulate a sort of instantaneous stellar generation in which all the stars in this hypothetical population are born at the same time, so all they will be coeval and distributed by mass according to the initial mass function, and also sharing a common metallicity. And of course, we know that the universe is far more complicated, and galaxies have complex and various star formation history. We know that there are galaxies that form, produce a starburst on shorter time scales, and they do so at irregular intervals along the cosmic time. There are others like spirals that form their stars at a steady pace for a very long time, gradually consuming the gas. But there are also galaxies like the most massive elliptical, which do not show any sign of star formation, and they also hint to have stopped star formation activity a long time ago. So another piece of information which is expressed by an analytical function which is quite arbitrary, I would say, at the time of speaking, is the star formation rate, for which we use to create the composite model convolving the contribution of this instantaneous burst. And I want just for the review scope of this lecture to at least mention a few that are widely adopted in the literature when analyzing galaxies. The first one that I want to mention is exponentially declining, where star formation declined with time following gas consumption, which was suggested by these colleagues, and it seems quite logically applicable to galaxy type like spirals. If you change the sign of the exponential, you obtain an exponential increase of star formation, which we thought in this paper was actually more suitable to describe the huge star formation episode happening at high redshift, and possibly also have informed the most massive elliptical galaxies. Then another question which I will come later on is how you actually conclude the star formation, which now colleagues use the term quenching to allude to this event. And you can either gradually keeping down to a very low level, like an exponential decline, but you can also envisage some mechanism to truncate it sharply, and then your function will be a step function. This model then gives you the opportunity to think about what is actually the physical agent truncating star formation, and AGN and massive black hole have been actually become very popular in the last years. So far, we have talked about the light, which is the integral of the emission of all the stars in our population. But we know stars don't live forever. So alongside in the same integral, in the same calculation, one obtain the emission of the galaxies, we also obtain a robust calculation and budget of what is the remnant population due to the stellar generation, be that an individual single burst or a composite event. And I would recommend you to look at this review book for modern physics edited by Stéphane Courtauld, where I have written the chapter on stellar populations. And this is one plot that is illustrative of the situation. If we start from a mass normalized, initial mass of your galaxy, of your stellar population normalized to 1, and let the time evolve, according to the initial mass function that we have assumed at birth, we will have a different evolution of the mass component of your galaxy, which is crucial for understanding galaxy dynamics, the contribution of dark matter, and so on. So a normal Milky Way light type of IMF, such as Salpeter, or more recently and more proved by observation, Krupa type or Chabrier type, will be reduced by roughly 30 to 40% in 13 billion years due to stellar evolution, gas ejection, and the rest will be locked into remnants, which can be of 3 types. The quest and the modeling of remnants has become, of course, very fashionable with the recent discovery of gravitational waves, because 2 of those are actually the most likely agent, the black hole and neutron stars. Here we are speaking about individual stars, and we do not enter any discussion regarding merging their existence in binary systems. This is also very important. I'm just giving you a number that come out of my modeling regarding which fraction of the total mass of a certain population we should expect in massive remnants according to the detail of the evolution. I will have the opportunity to give you a specific example later on in this lecture. Now, it is really important to acknowledge the progress that have happened over the past, I would say, 2 decades. This model have been enormously increased the quality of the input physics, the quality of the comparison about colleagues. And I would like to use these slides to give you one representative plot for what I consider to have been the most important developments over the past 2 decades, and it will happen that I'm quite involved in several of them, but there are many other colleagues cited in these slides. So probably the most revolutionary and spoken development was the inclusion back 20 years ago of the contribution of the thermally asymptotic giant branch phase, which is very difficult to model in stellar evolution and was thereby sort of neglected in the past due to massive uncertainties, several of which still exist. This is one plot that shows you the situation. If the black line is the spectral energy distribution of a hypothetical galaxy of 1 billion years, the red line is the same population to which we added the contribution of this phase, thermally passing asymptotic giant branch, which allow us to see for the first time important molecules and carbon absorptions, which are typical of stars in these phases, and also a sizable increase of flux, longward, roughly the optical, towards the near infrared. This was very important, especially for, and it has had much redundancy in analyzing high redshift galaxies, for the simple reason that TPAGB stars are energetically relevant in stars that have lifetime of about 1 billion years. Another revolution to which I was also very proud to participate was the inclusion, this one, of detailed chemistry in the models. Traditionally, the model before were taking into account the total metallicity of course, besides hydrogen, helium, but it was recognized, like in Milky Way science, that what is very important is the ratio of specific elements. And nowadays it's normal science, but it wasn't much when we first published this model back in 2003. And so the detail of the ratio of iron over magnesium, or the opposite, or the alpha over iron element ratio, where all the alpha elements like oxygen, silicon, and magnesium, and so on and so forth, are included. And this model, you don't need to go too deep in this plot, but just to show you that if I increase the ratio of alpha element over iron, proceeding this way to the right, the models finally are able to match the locus of massive elliptical galaxies, which was very important to study and include and derive the formation epoch of these galaxies. In more recent years, Charlie Conroy has done a lot of work also in this respect, and including the effect that, like we have done over the whole run of the SED, which is, as you can imagine, is far more uncertain, but it is the way we should all try to go. From the time I published my first model, we all made progress in increasing the spectral resolution of the model, taking pace with the observation, which of course are a much higher spectral resolution that we published back in 2000. So here, just as an example, you see a model that I published a few years ago, where the resolution is 10,000. We could go even higher, but then is not very useful for massive galaxies due to their broadening for velocity dispersion and a range of metallicity. These are models for the UV emission of galaxies, which are still very much based on theoretical spectra, as you can imagine in the UV. Another aspect that came up quite recently is the detail of the ultraviolet spectrum, not for young population, as you would imagine it would be very bright, it is, but for all the population. And this is important, especially to model the so-called UV upturn in all the elliptical galaxies. In this paper that I quote for a past student of mine, Claire Lecras, we have published models for a variety. Now this acronym only means different temperature and fuel consumption for the UV upturn emitters in the cores of massive elliptical galaxies. And then using large cosmological survey, we were able actually to understand that this UV upturn exists actually up to redshift 0.8. So this was, I thought, pretty impressive, and it relies on the goodness, let's say, of this synthetic spectra. I want to mention a field in which I have not worked directly, but it became quite important, and John Eldridge, I believe, was in Cambridge a few years ago, which is the inclusion of binary stars in the model. Actually, when I started my PhD and the calculation of this model, my supervisor actually advised me to stay far away from the problem of binary stars. Those were the time. The reason is that when you want to include binarity in a stellar population model dealing with clean stellar evolution of individual stars, you need to make a few assumptions, which may be realistic or may be less realistic. It is still nonetheless extremely important to explore them. In this paper, Eldridge et al. 2017, excuse me, compare their models, which are called bypass and are green in this plot, and in this plot with my models and with all other models from the literature. The effect of binary is expected to be more pronounced at very young ages, and also in general at short wavelength. Although you see different things in this plot, and I don't have the time to go into much detail. The only thing I would like to mention is that the fraction of binary has effects that are somewhat degenerate with the assumed rotation of massive stars. So it is an interesting understanding now how we can actually separate and calibrate those effects. Now, let me briefly mention the actually the most recent progress that has been made in the models. And when I say most recent is because this is, in fact, is something we completed in 2020, using the only good aspect of lockdown, that was that you cannot travel and you stay at home and work a lot. And these are the first population model based on this Sloan library, stellar library, that of course will be useful for many other things like detailed chemistry, stellar evolution, planet identification, a lot of good things. For us is to construct very sophisticated stellar population model spectra to interpret distant galaxies. What is the actual virtue of this library? As I said, the large number of spectra, the high signal to noise. Because of these huge numbers, we can actually remove and throw away poorly observed spectra. Due to the large number, they will have very small statistical errors. And very importantly for this spectra, they are being observed with the same telescope with which literally millions of galaxy spectra have been obtained, the Sloan telescope, but they have similar observational setup to instrumentation that actually they are already working or will be available in a few years. So we hope that this will remove an obvious discrepancy between the galaxy data and the model with which you analyze the galaxy. Also, the other important things, that they offer a wide wavelength range. It's not the widest you can think, but it is contiguous from 0.36 to 1 micron for the first time, and this part contains a lot of good features for the analysis of galaxies. This plot just want to show you, in comparison with the state-of-art library, which are the red areas, the golden areas is the age and metallicity we can reach now. Especially we can reach low ages, so just a few million years at metal poor regime, which are going to be very important for very redshift galaxies. Now, let me just give you a few examples of how we use the models, and in fact, I'm coming to the application of this model. This is a full spectral fitting, meaning that we match a model to galaxy spectra over the whole wavelength range, trying to find plausible solution. The new models that are the red here, the blue is another version of this new model based on different stellar parameters. Allow me not to enter in this detail. They give anyway very consistent results. You see the beautiful fit that we obtain, and an age of 7 billion years, and the metallicity a bit supersolar. With the model of the past generation, which were stopped at this wavelength, you see that you obtain younger ages for these galaxies. Now, of course, using a different wavelength range will affect the sampling of the stellar generation that you can have in a distant spectrum, but it is going to be very important to understand actually which is the most robust solution. The quality of the fit is absolutely identical, and from the chi-square you won't be able to understand that. We are fitting this spectra to the whole of the Sloan 4 galaxy data, which is, as you can imagine, a huge amount of data that we are making steadily available to everyone who would like to then use them to perform galaxy evolution. These are evolved galaxy. You see a spectrum typical of a mature galaxy. But thanks to Alice Concas, and I'm very glad I have the opportunity to work with her, and she's in Cambridge, we are also tackling the problem of modeling star-forming galaxies, not the emission line of them, which is difficult. However, we now can model the absorption continuum extremely well, as you can see from this plot that Alice sent me a few days ago, and I couldn't resist to show, because for the first time with this model, we find consistent solution in the H-beta region and the H-alpha region. And if you remember my introduction to the optimized population synthesis, which was used in order to make a good fit in small chunks of the spectra, it seems to me that with this new model, we will be able to find a physical solution alongside the whole wavelength regime of these galaxies. So, good progress here. But then, you know, these fit are beautiful, the chi-square is very small, they seem super accurate, but do we really know they give us the actual age and metallicity spread that it exists in this distant galaxy? How do you test these models? Well, testing models is something that was always at the core of my interest, because I realized in many years it's not too difficult with sophisticated computer codes and prescription to obtain good fits. But we needed to go deeper in this quest. So this old annual review by Renzini and Fusipecci laid down a method which we have always followed in our work, which is the following. The Milky Way offers a sample of globular clusters for which age and metallicity can be determined independently of the models. And in fact, one can determine the age through color magnitude fitting, as we know here, and the metallicity through spectroscopy of giant stars. And so in principle, we can calculate models that simulate these star clusters, obtain the properties of the model, and compare with what the resolved color magnitude diagram is telling us. And obviously, this exercise is very useful. It can only be done with nearby globular cluster, because any extragalactic globular cluster actually is behaving like a galaxy, in the sense that their properties are only obtainable through the models. So we have been testing our model against globular cluster for many years. And now let me show you our recent results, because thanks to the new models we make through the Sloan Library, the wavelength range of testing is larger. And also there has been a new database of globular cluster spectra from Asher et al., which very nicely matches completely the spectral range that we have in our model. And so here in the same paper I quoted before, we took this globular cluster Milky Way data and we fit them with the fitting routine. I will have the opportunity to get back to that. And you see example of young spectral energy distribution in the Magellanic Clouds, old metal-rich globular cluster in the galactic bulge. Look at the bands in the near infrared that are so pronounced. Intermediate metallicity, old globular cluster, old metal poor, almost featureless. So we took all this database of roughly 70 globular clusters. These are the numbers we can take. And what do we do that? We have obtained the properties of the model, and then we can compare with what was the color magnitude values that other people got. The comparison, what is telling us essentially is how close or how far the model extract from the physical parameter is to what other colleagues obtain through resolved color magnitude diagram, where you see the turn off. So the age cannot be, it is actually pretty robustly determined. There is one caveat to that on which I come back later. So the results have been exciting. This refers to our model, but now we are performing the same quantitative testing for models in the literature, which have not done this before. So with our new model, we get an age accuracy around 9% and the metallicity around 12%. And so this is really, to me, is the state of art. I've never seen numbers that are that small. And so this gives us a lot of confidence when we then take this model and we go extragalactic and we interpret galaxy redshift 5. So it is a very important exercise. Now, before going into the application, let me tell you that in fact, the numbers I show you so far refer to mostly to the model I have used, but it is well known that there are other colleagues calculating model and there are differences in the model. And I'm often asked in talks, so could you please summarize the difference? So I thought I make all of this in one slide. I take as an example of a model in the literature, the calculation by Brusoal and Charlotte 2003, because they are still representative from most other models in the literature, in the sense that they have similar, if not identical, input physics. They rely on the same evolutionary tracks, and they have identical recipes for the calculation of the integrals. So compared to my model, which sits at the other extreme, the following differences are found. Very young population, like 1 million year population, there is some flux difference due to actually my model adopting the Geneva tracks and the model adopting the Padua tracks in the phi UV. But the rest is pretty similar, up to the 10 million year, where there is the onset of the red supergiant phase. And it is well known in stellar evolution, there is a difference in temperature and the overshooting assumption in the two tracks. And this produced these differences in the DSCD. Proceeding in age, getting older model at 1 billion year, we have already spoken about it, and even more detailed discussion would deserve a separate talk. The most discrepant ingredient remain the thermally pulsing asymptotic giant branch recipe. And you see here, some models are redder than others, and my model are the reddest. The other bit of information is the core convective overshooting, which starts to be important in this type of stars. Finally, at old ages, now here the Brusoal and Charlotte is the green line. For a 10 billion year population, with respect to mine, they have actually a slightly redder SCD, and this is due to the temperature of the red giant branch, as it is described in the Padua tracks that they assume. And for the same reason, there is also a little bit of difference in the visual. They are more modest at a younger ages, although with the accuracy of the data we have at hand nowadays, these differences, also this is a log scale, are actually, they actually determine different properties for galaxies, as we will be able to see in a minute. I would also like to point you to the annual review, to the review by Conroy et al. Of a few years ago, which has, in fact, includes most of the things that I'm saying here. Now, there are three important applications of evolutionary population synthesis model. Obviously, the interpretation of observational data, but they are also important ingredients for galaxy spectra out of galaxy formation simulation. This has been at the core of my interest a few years ago, and I hope to be able to be back in depth. And I will be able to show you a couple of slides on that just. There is another fantastic application which regards cosmic chronometers using detailed ages of galaxies to trace actually the expansion of the universe. But I would like to mention it, but I won't be able to go to there because otherwise I'm going to not to stick to time. So now we want to compare models to data in order to use the model to obtain properties of data. As you can imagine, you can do this by having a fitting code that matches your model to the data and extract the parameters. We have calculated our own, we have prepared our own code, which is called Firefly, and I just refer to this is a iterative code that finds solution without assuming much priors at all, which turned out to be quite interesting in order to reconstruct instead of assuming the star formation history of galaxy. And this is all what I intend to do. This is one of the many codes available in the literature, and I will show you a few results based on that and other codes. So the most important use of the model from the observational point of view has been to actually derive fundamental scaling relation. They rely a lot, they rely half on data and half of synthesis model. And here I have to quote a fundamental work made by Roberto Maiolino and his team regarding the determination of the mass-metallicity relation, which is crucial to understand how galaxies form, grow their mass, and get chemically enriched. What I also want to stress in these first two plots is actually the effect of population synthesis model. To the left, you see the famous Peng Maiolino et al. 2015 Nature paper, in which the metallicity of galaxy is plotted against the stellar mass, distinguishing between passive galaxies and star-forming galaxies. This paper is based on certain data, but I think similar to those, or if not the same. But and the model of Brusol and Charlotte 2003. In this more recent calculation, again from Roberto's group, in particular led by James Trussler, which I bet you know, who has been obtained his PhD in Cambridge just recently, the mass metallicity relation has been revisited, changing models. In particular, in this plot, we use our model, and you see that while the metallicity mass relation for galaxies that are passive is well consistent with those. Now the scale are slightly different, but you can hopefully look at that. The star-forming galaxies instead show a different run, and in particular they have higher metallicity at the given stellar mass. Now, apart from this, they are both beautiful work. I want to stress that what you obtain through the data is also an effect, will be affected by the assumption you make through the model and the fitting of the data that you assume. Apart from that, this is a fundamental relation that has been found. Another one that probably has not been questioned much because of the sophistication of the model is the alpha-enhanced mass relation that we published a few years ago, which sees that the more massive a galaxy is, the more enhanced in alpha element is, which has been important to constrain the formation epoch of these galaxies. In this paper, led by Daniel Thomas, we have used the Sloan digital sky survey for Redshift 0, but Onodera et al. Have actually found essentially the same relation to be valid already at Redshift 2, which is fundamental for understanding the formation and evolution of galaxies. Very recent. Yes.
In 5 minutes, you can wrap up.
Yes, I will. I'm getting there. To the right, you see something that became very fashionable in over the recent year, which is another relation of galaxy, which is the IMF mass and radius relation. And this is from our own work, but this plot is good because it contains actually the data of those who have put forward this relation. First, Charlie Conroy, Peter van Dokkum. According to this relation, which is strongly dependent on population synthesis model, the most massive galaxies have a different IMF, which is more abundant in low mass stars. Another application that we are looking at right now, and I want to show it briefly because this belongs to the future of astrophysics, when I probably won't be active anymore. You can use this model to now spatially resolve the reservoir of gravitational waves. So the same way we obtain maps of age and metallicity resolved through the galaxy, we can then resolve the map of remnants. In particular, you see where I have the cursor, white dwarf, neutron stars and black holes and their mass contribution. When there will be detector that will look into distant galaxy for gravitational events, possibly this prediction will be valid. I have 3 slides to go. This was decoding observational data. Now we want to predict the spectra of galaxies out of galaxy formation model. I really don't need much introduction at Cambridge, but if you remember this slide from Carl Tombaugh, stellar population spectra are one of the main ingredients of galaxy formation models. And there are many researchers studying that. We have given our contribution a few years ago discussing in this series of papers the effect of assuming thermally passing asymptotic giant branch in different proportion and ingesting in a this was the galaxy formation model. To the left, you see simulation in observed frame colors of a redshift galaxy, redshift 2, colored with my models to the left panel, and to the right panel with the model without the TPAGB phase. And then without entering into a huge discussion now, but I may be during the question, you immediately see that these models are unable to cover the colors of the observed galaxies. But much more recently, and this is my last slide, another group around the Gulf-form code of galaxy formation model have re-examined, and instead of looking at one redshift, they have examined the whole set of redshift from local to high redshift using a large variety of models. Mine are the blue, Conroy are the red, Bruce Wall in various years of release are the black, etc. This is the K-band luminosity function as a function of redshift. And you see that while at low redshift, it is quite indistinguishable, the output of models, the more you proceed to high redshift, the more you see that, to be honest with you, only my model with their substantial amount of red thermally passing RGB stars can explain the data, while the other model fell short in all of them. What it is important is that in the V-band, the same model reacted the same way well, while the model that here was fitting in a degenerate way the data, which is the dotted line, which changes the recipe of dust, fail in the V-band. Why is this important to this talk? Because this is robust stellar physics that offers a natural solution to the cosmological evolution of galaxies. Let me leave you with this statement. While playing with the extra effect, like dust, that have a lot of adjustable parameters, actually in this plot cannot offer any solution, hence one of the many degeneracy is broken. Now, this is my last slide, Roberto, where this is just a simple summary of what I've said, so I don't need to read it at all. And so I thank you for the attention. I hope I didn't go too much over time, but being at home is difficult to control. And I stop here.
Thank you very much, Claudia, for this fascinating lecture. And I'm sorry again that you can't hear the clapping from people. And so people, if